Today I'm going to be showing you how I was learning Vulkan with Rust, and by the end of this video we'll have a triangle being drawn in a window. But even though this may not sound too impressive to you, the most important thing that we'll do today is that we are going to initialize Vulkan. This is going to give us a foundation to build a rendering engine on. So after we can add more complexity and render real textured lead geometry. And if you'll be inspired enough by this video to start learning Vulkan, which I'm absolutely hoping for, then you might be interested in joining our Discord server. There you can ask questions or simply chat with other Vulkan enthusiasts. I'll be hoping to see you there. The link will be in the description. Because Vulkan was originally written in C, we need some sort of wrapper in order to conveniently use it in Rust. For that purpose I prefer using Ash. There are many other wrappers, but Ash is good enough for us. First we need to create a Vulkan instance, that is, giving our program a way of interacting with the API. As you can see, instead of just putting all of the code into the main function, I've created a structure. That's because I don't want this project to instantly become a mess, and maybe I can keep this trend, and maybe one day this will become a featureful game engine. Here you can see that I'm using an unsafe block to call an Ash function. That means that Ash is unsafe, but that's not a problem because we're going to safely wrap it around in our engine. All unsafe essentially means that we can call unsafe functions and dereference row pointers, but that's not really of our concern here. When creating an instance we can pass in some parameters, for example the application name or the engine name. However, that is mostly needed for AAA games, so that the driver can adapt to a specific engine. The most important parameter for us is the API version. I'm going to be using the 1.1 version here. If we run the program right now, we're going to see no output except for some warnings from the compiler. In order to set up debug logging, we have to do some additional work. Here you can see the debug function. It may look scary, but it's nothing difficult really. All it essentially does is casting pointer to a string and printing it out. Here is the implementation of the render debug structure. It's a little structure which purpose is to initialize everything debug log related. Not much is going on here except for one little thing to which I'll return later. Running the program now gives us our so wanted debug logs, and we even already have an error to fix. There's actually a hint on the screen on what we need to look into. It said that the cleanup function was never used, and that's exactly what the issue arises from. The problem is that we have to destroy everything we create manually, just as one would do that in C. We also have to preserve a specific order of destruction. So, for example, if we first create an instance and then create a debug utils messenger, we have to first destroy the debug utils manager and then the instance. So it's basically the reversed order of creation. So first we destroy the debug utils messenger. I'm doing that in an associated function. Then this function gets called in the drop implementation of the Vulkan renderer, and right after the instance gets destroyed too. And with that we have debug logging set up and no errors in the output. Now we just need to keep initializing things in the same manner and nothing terribly bad should happen. The next logical step would be to pick a physical device. A physical device is basically how Vulkan refers to your physical GPU, or a bunch of them. Yeah, in Vulkan you can work with a bunch of GPUs at once, which is pretty handy when you need to compute something. We can enumerate all of the physical devices and choose an appropriate one. For now I'll just pick the first discrete GPU we hit. It should be fine for my machine and I don't really care for other machines for now. The next step is to create a logical device and get ourselves some queues to work with. Actually, we'll only need one queue for now. A device may have many queue families, each of them containing queues capable of executing certain types of commands. To each queue you can send commands from different threads, but it's not guaranteed that the commands will be executed simultaneously. Physical device is now stored in the render device structure, as well as its logical representation, and the only queue we'll need today. Picking physical device was also moved here, and the next bit of code is just looking for a queue family that supports graphics commands and finds its index. Then we again prepare a bunch of builders and finally create a logical device, and then get a single graphics queue just before returning. I don't know if you've noticed, but we've been missing something very important all along. I think you've already guessed that it's a window to draw in. Well, actually Vulkan does not require you to have a window. We could have been rendering into an image and then saving it into a file, but here we want to do real-time rendering, so a window is crucial for us. This function is responsible for window and event loop creation. They are both an important part of window handling. I'm also giving window a title because I didn't like the default init window one. Then I'm simply returning both event loop and window. As window creation is OS specific, we would have to do additional work in order to support multiple operating systems. But thankfully we have an Ash window crate, so here I'm simply calling an enumerate required extensions function, passing in our window and iterating over it, adding each extension to the rest. The window ends up being stored in the render window structure, as well as some other stuff that we're going to initialize right away. Nothing complicated is going here either, since Ash window is doing everything OS specific for us. We're just creating a bunch of things and then returning. Also, don't forget about cleaning up. Now, having a surface that is a window is not enough for drawing. We also need to have an image to draw into and then to present onto the surface. That's how it works, and that's what we'll be working on right now. Though having only one image is usually not enough, because your hardware would be idling a lot, and the performance would be only a fraction of what your hardware could possibly provide. So, how would a system with a non-singular image mount work? Well, there are many ways of implementing that, but let's only consider the one we'll be using here, at least for now. In Vulkan, this job is being done by Swapchain. It has many present modes. We'll be using FIFO. It means first in, first out. Let's say that for now we have only one image. The first step would be to render it. After it's rendered, we can present it with the next vsync cycle. And while it's being presented, our hardware is idling. When the presentation time runs out, we need to render the next frame. If we fail to render the next frame until the next vsync cycle, we have to wait for the next one. And after it's rendered, we present it with the next cycle. And this process goes on and on. It's clear that with this method our hardware is idling a lot, and we could have processed many more frames while presenting. The other two problems with this method is that if we skip a vsync cycle, then we have to wait for the next one. And that's virtually dividing FPS by 2, and if we skip another one then by 3, which is no good. And the last one you might have noticed, it's that when we are rendering there's nothing to be presented, so the user would just end up seeing black screen while we are rendering. In real life it would look like the screen would just keep flickering, changing between frames and black screen. What happens if you add in another image? Well, now we can render the next frame while still presenting the old one. And if we're done rendering while still presenting, we simply put the next frame into a queue. So in this case our hardware is idling a lot less, or ideally not idling at all. That was a long one. Hopefully my explanation was somewhat good. Anyway, let's set it up. Because swap chains, just as windows, are optional, we have to enable them with an extension. But unlike surfaces that is windows, swap chain is a device extension, not an instance extension. So we have to pass it in while creating a logical device. Here's everything we need from swap chains for now, and it's stored in a separate struct. All the data needed for Swapchain creation is prepared here. And we can finally create a Swapchain. We'll be using 3 images, but at least the minimum amount and at most the maximum amount our device supports. The image usage flag is set to color attachment. That means that the images will be used for rendering. And the present mode is set to FIFO, the one we discussed earlier. We can now get all the images from our Swapchain, but we can't work with them directly. We need an image queue for each one of them, and creating this is what this code does. Then we simply return everything we've created. And in the cleanup function we first destroy all of the image views and then the Swapchain itself. The next step is to create a RenderPass. RenderPasses essentially consist of 3 main things: attachments, subpasses and subpass dependencies. Attachments are essentially the images that the Swapchain is giving to us, though we can configure what to do with them on different steps of rendering. So for example here on load OP we say clear and on store OP we say store. That means that when the image is loaded it's going to be cleared, and when we are done rendering it's going to be stored somewhere so we can present it. Stencil load and store are out of our concern right now. And the sample count flag is 1 because we are not going to use any multi-sampling here. Now we are setting up a slice of attachment references. We have only one reference to the first attachment. Now we need to set up subpasses. In the subpass description we pass in the color attachment references and the bind point. We are going to bind at the graphics point. And let's talk about why for complex rendering we need more than one subpass. The problem is that when we're rendering we can't access the attachment we're rendering to, so you can't know what's already been drawn, and knowing that is required for some effects. Next we set up subpass dependencies, that is how subpasses correlate to each other. We have only one subpass, so there are no dependencies basically. And then we finally can create a RenderPass and store it. We also need to create a frame buffer for each of the Swapchain images. Their purpose is to simply connect Swapchain images to the RenderPass attachments. I'm not going to stay here for long because nothing difficult is going in the code. And we finally got to shaders. Although we're not going to write any shader code just yet, we need to load them. We have a vertex and a fragment shader and they're both empty. If you don't know, shaders are the programs that are being executed on a GPU instead of a CPU, and they are usually used for placing vertices, deciding what color a pixel should be, or simply computing something. To represent shaders I've created a little struct that holds everything we'll need, as well as a function for creating a shader from its code. I've also coded a couple of convenience functions so we can create specific shaders more easily. And there's also a function to get the shader stage create info from a shader. We're going to need it when creating a pipeline, which is going to happen right after I show you the cleanup function. And it's simply destroying the shader model, so let's move on. Let's now look into what it takes to create a graphics pipeline. Once again, here's the structure that holds everything we'll need. We first create all of the shaders we'll be using with the help of the struct we've just discussed, and also the include GLSL macro. It's a very useful macro that compiles source GLSL code into SPIRV binary at compile time. We then turn the shaders into a shader stage slice. Next we configure the states our minimal pipeline will be going through. A typical graphics pipeline contains a set of states which are being executed consecutively. Not all of the states are configurable though. The first state is input assembly. It's the state where primitive topology is being assembled from the data we're giving to the GPU. We could have been rendering points or lines, but here we're going with the triangle lists. Next, the vertex shader is being executed, but right now it's empty. Viewport essentially specifies what part of the screen we're rendering into, and rasterizer returns points to actual pixels. The polygon mode is set to fill, so we'll be getting filled triangles. We could also say line and would be seeing only the outlines of the triangles. It may be useful for debugging, but let's save this for later. Multisampler says how many samples we should make for one pixel. Here we'll be doing one sample for one pixel, so no multi-sampling basically. And after sampling, the fragment shader is being executed. It's also empty for now. And the final step is color blend. It defines how the new just rendered color will be combined with the old one that we already have in the frame buffer. And that's it for our minimal pipeline. We may still return here later to touch all of the different states deeper. And after the pipeline is created, we can clean up all of the shaders and return. In order to submit a comment to a queue, you first need to record it. And in Vulkan you record commands into command buffers. So let's create one. Command buffers are being created from command pools. So we first need to command pool. Here's the structure that will hold all the command pools we'll be using. For now it's only one. While creating a command pool, we need to specify what queue it'll be created for. In our case it's going to be a graphics queue, so we first get it from the device. We also set the reset command buffer flag. It means that we can record a buffer, submit it, then reset it, record it and submit it again, and so on. That's so we don't have to create a whole new buffer each frame. I've also created a function for easily allocating command buffers from a pool. Here we're just filling in some structures and invoking some Vulkan functions. And in the cleanup function we are destroying the command pool. I'm then using this structure as follows. I'm first creating an instance of it. I then create a bunch of graphics command buffers. The count is equals to the frame buffer count in the Swapchain. I then fill each of the buffers with commands. First we begin the command buffer. It requires no extra parameters. Then we specify the clear values. This is responsible for which color will appear on the screen where there's nothing to render. We then need to begin a RenderPass. We specify everything required, including the clear values, and then call the cmd begin RenderPass on the logical device. We then bind our pipeline. And then finally we record the draw command. A triangle consists of 3 vertices and we'll be having only one for now. We then end the RenderPass and the command buffer. Although we've just recorded draw commands, if we run the program right now, a window will appear for a moment and then it'll just collapse. That's because we never actually submitted any of the command buffers we have. At this point we are pretty close to drawing a triangle, so let's just do this. But first we have to spare some time on talking about synchronization. Because Vulkan is a parallel API, understanding it is crucial. Parallel means that we can record command buffers and submit them to queues in other threads, not only the main one. Although these commands are not guaranteed to be executed simultaneously, it's still very likely. There are many synchronization tools in Vulkan, but we'll only talk about 2 of them for now. Fences and semaphores. They are pretty similar, except fences are used for GPU to CPU synchronization, so a GPU may signal when a CPU may continue its work. But semaphores are different, they are used for GPU to GPU synchronization. So a GPU might wait for some GPU work to complete before continuing to work on something else. In our case, synchronization is needed just so we don't end up presenting an image we're still drawing into. Because sync structures in this case are connected to the swap chain, in a sense that one frame buffer should correspond to one sync structure, they'll be stored here. Creating 4 structures require no extra parameters, except all of the fences we'll be creating will already be signaled. That's so our program doesn't just halt on the start. Because fences here are responsible for saying are we allowed to draw yet? And at the start if it won't be signaled then nothing will happen. And in the cleanup function we also have to destroy all of them. And the last thing left to do is to execute everything we've been setting up for the last 18.5 minutes. We first acquire the event loop from the window, because otherwise it just won't work due to some lifetime issues. Maybe there's a better way of fixing this, but I don't have enough experience in Rust to do this. We can now run the event loop like this. It'll contain a single statement matching on the event. For example, if something attempted to close a window, we can tell to the control flow to exit. We could have also done something additional, but we don't need to do anything here. The main part of it is of course redraw requested. It's where all of the drawing logic will be. Let's finally get started with drawing. We first bump the current image counter on the swap chain, just so we know which image to draw into right now. We then acquire the next image, setting it up so the appropriate semaphore will be signaled when it's available. We then wait on the may begin drawing fence and reset it, so we don't end up drawing the picture if we are not supposed to do this at the moment. We then submit an appropriate command buffer to the queue, the one corresponding to the image we're currently drawing into. We also wait on the image available semaphore and signal the rendering finished one, and we finally present the image we've just drawn into. Now we actually have to write some shader code. It's not going to be very difficult though. So in the vertex shader we define an out variable named oColor. It'll define a color for each vertex of our triangle. For position we're using the built-in GL position variable, so we don't have to define our own. Out means that it's going to appear in the fragment shader as an in variable on the same location. We then define a position and a color for each of the 3 vertices we have. And in the fragment shader we have an in color and an out color, we're just equating them. So a color of the vertex is going to be the one defined in the vertex shader. And with that, if we run the program now, we are finally going to see a triangle, a colored one. And that's all it takes to draw a Vulkan triangle. I hope you enjoyed this journey, because I did. But it would be nice if you enjoyed it too. Hope I'll see you again in the next video. But for now, goodbye.